So as you can tell from my resume, I've had a hard time finding a job. But now I've got a good one. So the previous couple people have talked a lot about what the machine learning is and how you analyze these complex data sets. And I'm going to talk about a particular type of data set, and that is hyperspectral imaging. And so Headwall Photonics, that's our basic product is that we make these hyperspectral imagers. We started out making diffraction gratings, and I'll try and tell you about how diffraction gratings can be used to make these spectral imagers. So because I'm a physicist, I have to start with the spectrum, and of course it goes from gamma rays, which are very high energy, down to AM radio, which is very low energy. And then in the middle of it is what we're familiar with as light. And the basic way I look at it is each of these the photons is a little bundle of energy, and it's going to interact with some system that has a similar level of energy. And if you look at the electrons running around inside of an atom, those are going to have fairly high energies. They're little things going around really fast. And if you look at the two atoms inside of a molecule, they're going to have somewhat lower energies. And we will see that here in the ultraviolet, you'll start to see things like atomic lines, the lines of atoms. Of course, we're all familiar with the sodium street lights. Those are atomic transitions. And then as you get on from into the red and the infrared, you start to see things associated with the motions of molecules. And the basic point is any given atom or molecule is going to interact with certain colors of light more than others. And so if we can tell what is the light that is either being emitted from, transmitted through, or absorbed by a thing, we can tell something about what that thing is. And that's the basic science of spectroscopy. And so what we do in this hyperspectral imaging, there's a bunch of different ways to do it. And the way that Headwall does it is we start with a slit. So we're looking at the world through this little slit. So we see this one little line of the world. And then that slit is re-imaged through some mirrors. One of those mirrors happens to be a diffraction grating, like a CD. It's something that's going to break everything up into a rainbow. And so that one image of the slit gets broken up into many images of the slit, and those are all put onto a focal plane. So I take one photo from one image from this focal plane, and what I have is an image of whatever I'm looking at. Let's say it's someone's eyes. I have it at hundreds of different colors. Same spatial information, but just done over and over and over again in many, many different colors. And so by taking that slit and then scanning it across the world, I can build up an image, and every pixel in that image will have hundreds of spectral data associated with it. Another way of looking at it is I can take a scan, and I'll be able to show you all a system that I have out there that will actually take some scans. I can take a scan, and each one of those scans will develop several hundred different pictures. They're all grayscale images, but each one says, this is what the world looks like at this wavelength. This is what the world looks like at this wavelength. This is what the world looks like at this wavelength. If it all goes dark at a certain wavelength, you say, aha, that's the absorption band of whatever that chemical is. And particularly if anybody who's worked in the infrared, they know you can't see really anything around 4.5 microns because CO2 absorbs everything. And there's similar absorption bands from the atmosphere. And then you can also see other things, and you can start to see things like plant stress, different phenotypes, and contamination, all those sorts of things. I'll talk a little bit about some of that. And so our systems, you can actually, depending upon the fore optic that you put onto the system, you can see pretty far. We have these things in space. We have these things looking at conveyor belts. I have one sitting on a tripod out there. We fly them on UAVs. You were talking earlier about ground spatial resolution. Now I've recently started working with the UAVs in the backyard of our shop. I can easily get 2 centimeter resolution with this. Of course, it takes a long time, and I can't get the large spatial coverage. And so here's basically what I want to talk about mostly is a few examples from what we can do in terms of analyzing food. And some research that was done before I was involved with the company is by keying in on certain spectral features, we can say something about what are histamine levels in tuna. And then about a year or so ago, my colleague Basil and I looked at some stuff we had in our cafeteria, some chips and some chocolate bars. And I said, well, what can I tell? Can I tell what's in there? And I learned some interesting things, and I'll tell you a little bit about what I learned, particularly about the chocolate bars, and use that as an example that's not proprietary of what we can do with this sort of stuff. Because in general, we'll work with our customers, and they'll say, yeah, well, we own all these spectra. You don't tell everybody what we're doing. Well, I'll tell you what they're doing, but not how we're doing it. Okay, and so basically, what we'll start with is we'll generate what people in the remote sensing call the ground truth. So we'll take some data, set up the spectral imager. Once again, remember, it's taking many, many, many photos at many, many different wavelengths, or alternatively, each of the pixels has some spectra associated with it. And there's a simple way of doing this sort of stuff, and I'll talk a little bit more about it, called spectral angle mapping. But basically, it's not artificial intelligence, it's my intelligence, or it's the user's intelligence. And I'll say, this example right here is olives. That's olive meat, that's, over here is olive skin. And I'll click on a pixel and I'll say, hey machine, this is the olive meat. And it will say, okay, here's all the pixels in this image that look like that, within some bounds according to some criterion that I set. And then we'll average all those together, saying, well, maybe each one of the pixels that we have is kind of noisy, but if we take an average of 10,000 of them, we're going to get something about what's really going on, and that's probably going to represent, going back, the chemistry, the atomic composition of the stuff that we're looking at. And so we go through that, and we try and build up a spectral library of each of the different things that we're going to look at, and then, not from the stored data, from actually looking at new things, a scan of a field, a conveyor belt sorting almonds, and we'll be able to say, this thing right here is most like this guy in the reference library, this guy in the reference library. And so this is, once again, I don't know if you can read, I have black paper shadow, Milky Way chocolate 2, Snickers nougat, Three Musketeers nougat, Milky Way caramel. Each of these different materials that I saw inside the candy bars actually have different spectra. Now, I could actually probably do some, I'm pretty sure this is a water band. We can do some chemistry. We don't really need to, because what we want to say is, well, what's this most like? I gave you some background. I trained the system. What are the things that are most like? And we use this technique, and this is, in some sense, a simple way of doing the spectral analysis we call spectral angle mapping. Now, this is a field that's a rich field for doing machine learning. In my work, I've had a lot of success doing it kind of in this kindergarten way, and you can get a lot out of it, and I'm sure that as we go further, and maybe somebody here is going to partner with me to help develop sort of these machine learning algorithms to do, I don't know, principal component analysis, linear description, all these different types of statistical methods by which you can take, because remember, each one of these curves is, in this case, 370 different data points. So we want to say, certainly it's the case that this curve right here is very different from this curve right here. And some of these curves have quite a bit of a dip here. How do we say that one looks like another? So our brains have evolved to do that. I mean, but our ancestors would have died if they weren't able to find food. But getting a computer to do that is actually kind of hard. And so this technique of spectral angle mapping, and I'll be honest with you, don't really understand this, but basically, you think of a thing of a vector, and it's a line pointing out in 3 dimensions, and another vector is a line pointing out in 3 dimensions. And I can do some math on x and y and z, and I can calculate the angle between these two things. We all did this in geometry before. Okay, well, I can do that in 2 dimensions. I can do it in 3 dimensions. Why the heck can't I do it in 370 dimensions? It's the same math. And 2 things that have about the same shape are going to have a small spectral angle between them. 2 things that have a very different shape will have a big spectral angle between them. And so we'll generate this reference library, and that, again, is generated by looking at the data, choosing all those pixels that match the spectral angle of the pixel I chose, and that's what each of these curves, it's an average of several thousand different pixels from the reference set. And then we go for each pixel now and say, what is it most likely? To what does it have the smallest spectral angle? And so when I looked at these candy bars, one thing I learned was when I do the classification, it's not clear from looking here, but it's pretty clear from looking here. When they make a Twix, they dip the cookie in chocolate before they put the caramel on top of it. And you can tell because there's some classification of chocolate right in here between the caramel and the cookie. Okay? Oh, that's pretty neat. And the nougat in a Milky Way and a Three Musketeers is pretty similar. Well, yeah, I always figured that. And then Snickers have peanuts in them. Well, yeah, it's okay. So that's not a big deal. I can certainly find the peanuts. But man, if I look over here, I've got peanut as one of these white colors. There's a bunch of white down here in the nougat in the Snickers. What's up with that? I worked at it, couldn't get it to work. I look online for a recipe for making Snickers at home. Well, you make nougat and you mix peanut butter in with it. And if we look at the spectra here, these are now normalized spectra. So we're not concerned about how bright or dark it is. We're concerned about just the shape. Well, that's what the spectral angle mapping does. This is Milky Way and Three Musketeers nougat. It's pretty much the same. This is the peanut and the nougat from the Snickers, and except for this little difference here in the very short wavelengths, they're almost identical. And so, in some sense, I learned something by doing this analysis. And so that's the data that belongs to me that I can show you all. And I'm going to run through a few examples of how people are actually using this sort of stuff commercially. And so the first one is we've been working for a few years with Bratney Companies. They're basically a seed processing company out of Iowa, and they do big industrial installations. And they came to us and they said, well, can't you do this sort of spectral analysis to sort almonds? And so, once again, build up a spectral library. This is a good almond. This is a dark almond. These are almonds that basically were left on the tree over a year, and they sort of rotted a little bit. Sometimes people, if they're making almond butter, it doesn't make a big deal. If you're selling it to the Japanese, you can't sell them those. This is almonds that are still in the shell. These are split almonds. Once again, sometimes it's okay to have the exposed almond meat, and sometimes it's not. And then this is insect damage, and these are almond hulls. And we do the false color. We do the spectral analysis pixel by pixel, reassemble the image. The blue is almond. The yellow is exposed meat, and various different other colors for the various different things. And these systems are running. We've got several installations in California. You've got these hoppers that are feeding in. I think these are like 5,000-pound bins. Systems, each one of the systems will run about 2,500 pounds of almonds an hour. They'll go through a spectral imager. The classification is done in real time. Belts traveling about 40 feet per minute. And then the data from the hyperspectral imager is sent to a robot. The robot has a vacuum thing, and it goes and sucks out all the stuff that's not almonds. And they run 24 hours a day, and they actually do a really good job. It's quite impressive. One other thing that I want to talk about is we're interested in reflectance spectra to do this sort of stuff. And so you're going to have this is an active imaging system. So you have to have a light, but the light isn't white. Right? It's going to have color. It's going to get a variety of different colors. And then the detector is not going to have a uniform response. And so what we'll do is we'll look at, and then this automatic system, this little tile flops down. We take a picture. You say that's white. And then we take all of our data, we divide it by the spectrum of the white, and that calibrates out the responsivity of the detector and the spectral characteristics of the source. And then we get towards reflectance spectra, which if you go back, that's what the atoms and molecules are doing. They are absorbing or reflecting, and so this reflectance spectrum is what we want. And once again, these things, it's amazing to watch these little robots all day long. Okay, and then we have done some work in the past with the Lemnitech folks, and I haven't personally, but a lot of these different things about telling different characteristics of plants you can do using this spectral analysis. Probably not using the sort of simplified spectral angle mapping technique. This is where what we can do is we generate these rich data sets that you can then use for your machine learning. So I'm going to give you two more examples of how this sort of stuff work through some collaborations that we've had with the U.S. Department of Agriculture. And one of them is looking at apples. Okay? So they're looking at apples. They want to see apples that are going to be used for juice. And there's a couple things they want to see. Do they have bruises on them? And do they have bacterial contamination on them? If you're squeezing it for juice, you don't want any E. coli in the juice. And doing some research, these folks found that, well, you can see the bruises by visible reflectance, and you can see the fecal contamination by fluorescence. And so looking at reflectance, it's the normal apple, these bruise defects, and then each one in these experiments had a small fear of bovine feces on them. And in the near infrared, there's some really big differences between the normal and the bruised apples. And in the visible part of the spectrum, there's a really big difference between the fluorescence of the normal and the fecal contamination. And so the whole thing runs through one by one. I'm giving an example here of a simple, very simple classification for finding the fecal contamination, and it's pretty good at getting every one of them. And then something similar you can do to detect the bruises on the apples, and then you can generate some fused data and say, good, 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 good. This one, you know, it depends on what the grade of your product is. Maybe you can take some bruised apples, but you never, ever, ever want any with the fecal contamination on it. And then one more example, and I believe there's some stuff. There's some patents through the USDA on this. And then also poultry, same sort of thing. In this case, they were looking for septicemia infections in the birds by examining the carcasses. Once again, looking at a spectrum through it all. And this is an example of, as I said, one way of looking at the hyperspectral image is that you have a spectrum for every pixel, and another way of looking at it is you have an image at each wavelength. But in general, we're going to be doing the spectroscopic analysis, and what they've done is generally someone else had already said, okay, that guy had septicemia, that guy didn't. There's differences in the spectra. You do some work. Once again, you can do it by people. Like, I think there's 2 or 3 different important things that I can find here, or I think probably better done by some machine learning algorithm. Give it a big data set. Tell me what I should be looking for. And they've developed some features for this and got some very, very nice results compared with examinations by a veterinarian in the plant. It's my understanding that when you're processing poultry, you actually have to have, you know, a certified person looking at every single carcass going by because you really want to control the infections. And so I think I'm just about out of time. So I'd really like to thank our partners at the USDA, particularly Moon Kim, and the guys at the Bratney companies who've worked very hard with us in developing all this technology. And that's it. Thank you very much.
Thank you, Carson. We do have time for some questions.